Hello, stats class. Here's lesson 10.2a, which is about comparing two means. This lesson is not on the quiz, which is for 10.1, so if you need to put off these notes till after the quiz, that is fine. So comparing two means, we're switching into, we still have two populations. We still have two samples. Instead of calculating p hat or proportions of something, we'll be calculating means of something because now we're working with numeric data or quantitative data. So we'll be calculating our x1 bar and our x2 bar from the two separate samples. And then we're interested in talking about the sampling distribution of the difference of two means, which is x1 bar minus x2 bar. And it's the same basic idea, except with means. So what happens with that, we're going to do the same structure as we did in 10.1. We're going to start with the sampling distribution and what if we know something about the population. And then we're going to move to confidence intervals and significance tests later, like later this week. So the sampling distribution, we need to talk about shape, center, and spread. Shape, well, we hope it's approximately normal. You might have guessed that that will happen some of the time, right? It will happen if both original distributions were normal. So since we have two populations, if both the populations are normal, that would be great. Or if both sampling distributions are normal, that would also be great. So this could be given to us. Or we might have that N1 and N2 are greater than or equal to 30, and then we could just not worry about the shape. Or we could check the graphs. So remember, this is the part where we don't do the NPs anymore. We do all these different possible things that could happen. If the graphs are not too skewed, then we're going to be okay with that. That's the 15-30 rule, where if it's in between, then a little bit of skew is okay. And if it's less than 15, we really don't want it to be skewed. Or what's fun about this is we've got two different distributions. Excuse me. Any combination is fine. So if you have one population that's given as normal and the other one you have to check the graph or something like that, that is just fine. So you check each sample separately by whatever method you need to get it to be normal. Well, to check to see if it's normal. Separately, I think I spelled that right. Yeah. Okay, center. Once again, we're hoping it's unbiased, and it is normally naturally unbiased. That would mean the mean of x1 bar minus x2 bar would be the same as the mean of the first population minus the mean of the second population. That is going to be true if we do our sampling correctly. So it's unbiased if we do a random sample or randomly assigned treatments. And so that's going to be the random condition that we've done so many times before. Spread is if they're independent, right? And it's going to be a lot like what we did with the proportions, where we're doing the sigma of x1 bar minus x2 bar. And I'm remembering what we did in chapter 6 with difference of two random variables. You can use the Pythagorean Theorem thing. So we can do this thing with the two standard deviations of the two populations. Actually, not the populations, but sampling distribution of x1 bar compared to the sampling distribution of x2 bar. Those two standard deviations can be combined with the Pythagorean theorem. And we're going to simplify this like we did with proportions. This is not the formula we usually use. Usually we replace both of these with what they equal. So let's do that. I'm making it taller on purpose because you might remember that this is sigma over square root of n, except we really should put 1s on both of them. And this is sigma over square root of n, except they both have 2's on them. And then the squared and the square root can cancel each other out. The top needs to be squared, but the bottom does not, to make this a little bit simpler formula. So sigma squared from the first population over n1, you don't need the square root and the squared on the bottom because they cancel. And then same thing over here, sigma 2 squared over n2. That's the formula we're going to be using. It's the simplified version. So all the stuff up above is just showing you where this formula came from. So this is the derivation or where it came from. This is the formula that you need. And this whole thing, all of it is true if the samples are independent of each other. And also if the 10% rule is met for both samples. So N1 is less than 10% of its population, and second sample is less than 10% of its population. So all of this is true if this is true. All right, so this all should not surprise you a bit. I feel like the repetitiveness of this chapter is going to start to help you because it should sound so much like what we did with proportions. It's like almost the same thing, except we're just shifting to means, and I hope none of that surprised you at all. So we're going to start, like I said, in 10.2a, we're just going to start with if we know the population information. So that's if we know sigma 1 and sigma 2 and mu 1 and mu 2, we can find some probabilities from that. And then we're going to shift to what if we don't know the population stuff on Thursday when we do 10.2b. So that's coming. So let's do an example of that. It should remind you of the example we did in 10.1a, and it should also remind you of some stuff we did in chapter 7. Let's talk about 10-year-olds and their heights. And we're going to look at girls versus boys. And I don't know if you remember being 10 years old. That's the age when the girls are mostly taller than the boys because they have their growth spurts earlier and then the boys catch up during middle school, right? So at this age, the average height for girls is bigger. Also, the population information here is given. And here's the population information. We're given that the girls' heights are approximately normal with a mean for girls. I'm going to call it G instead of 1 because it's easier to keep track of that way. Mean for girls is 56.4 inches, and standard deviation for girls is 2.7 inches. And then for boys, they're also approximately normal. And the mean for boys is 55.7 inches. They're not that far behind, right? And the standard deviation for boys is 3.8 inches. All right. That's the information that's given to us. We're going to use that to find a probability. So let's suppose we take two separate random samples. Of 12 girls and 8 boys, all age 10. And we want to know the probability that this particular sample has a smaller mean for girls than for boys. Probability that the sample mean for girls is less than the sample mean for boys. All right, so in symbols, it looks like this. It's the probability that x bar g is less than x bar b, which is the same as saying the probability that x bar g minus x bar b is less than 0, given all of this information up there, which I'm not going to write out again. Okay, so what we're doing is we're looking at the sampling distribution of a difference. Yeah, so we're going to use this information right here to find the center and the spread of that sampling distribution. And then we're going to do a z-score and a normal CDF because we know sigma, so we can use z, and that's going to change on Thursday, like I said. So center is the mean of x bar g minus x bar b, and we're going to go with what we did up above. So the mean of the difference in sample means is the same as the difference in the population means. So that's the same as the mean of the girls minus the mean of the boys. Okay, so I could do that. That's pretty easy. It's 56.4 minus 55.7, which is 0.7. Not a big difference in means. The spread is sigma x bar for girls minus x bar for boys, and that's this messy formula that we just wrote down. So we're going to use that formula with the square roots in it. We can handle it, and we're going to use these two standard deviations divided by square root of n, and then squared and added together and all that. So we're going to, actually I might not have room, but I think I can. 2.7 squared over the sample size for girls is 12, and then I'm going to do the same thing with the 3.8 squared over the sample size for boys is 8. That's what it looks like with the numbers plugged into the formula. If you type that in your calculator, you should get square root of 2.4125, which is 1.55. So I'm using what I know about the shape, center, and spread of the sampling distribution to calculate these because I'm going to need them for my z-score. So to find this this probability, I'm going to find a z-score by doing the difference that I'm interested in is 0, so that goes first, minus the difference that I think is true about the population. So sample minus population divided by my standard error. Actually, this one is probably called a standard deviation because it's not from the sample, it's from, well, it's from the population information, yeah. So if you calculate all of that, you get a negative 0.45. And then remember, we're picturing a normal curve with the center of it at 0.7. And so like about here is where we're at, and we want to find this probability of being less than that. Wait. This is where the 0 is. Z-scores would be 0 here and negative 0.45. That's right. So this is the difference in x bars. This is the z. Okay. So then we're going to do normal CDF to find the probability. Probability that z is less than negative 0.45 is officially normal CDF. Negative 999 and negative 0.45, and that is 0.3264. This is not at all unusual to have a small sample like this have the girls be shorter than the boys, even though overall the population girls are taller. This is not unusual. And then, of course, in 10.2b, we're going to do confidence intervals. 10.2c, we're going to do tests for this same basic concept, but not yet. So I think that's enough for today. Population, find the probabilities.